Hi friends, let's continue our discussion on the machine learning algorithms. Now let us see three basic algorithms on the machine learning. The three algorithms we are going to look at are the linear regression, k nearest neighbor, and k means. The linear regression, so assuming that there is a linear relationship between an outcome variable, sometimes also called the response variable or dependent variable or label, and a predictor, sometimes also called independent variable, explanatory variable, or feature. So, in short, here if we assume that there is a relationship which is linear between output and input, then we can represent this relationship as y is some f of x, where f of x can be a linear relationship with respect to x, can be represented with beta naught plus beta 1 times x. So that's a well-known equation for a straight line. So if it doesn't look familiar, then let us get our old version, and it is called y equal to mx plus c. Here, so m is replaced with beta 1 and c is replaced with beta naught. So beta 1 talks about the relationship between y and x, that is the slope of the function, and beta naught talks about the intercept where it crosses y, that means when x equal to 0, the value of y. So the aim of linear regression is, if we are given with a set of xy pairs, then we need to identify beta naught and beta 1 that satisfy the above equation for all the data pairs. So once this beta naught beta 1 values for the given data set are identified to the required accuracy, now we can use these values to predict new values of y for any given value of x. So that's a logic of linear regression. So we have a big set of data, that means xy pairs, maybe in terms of millions, and then this whole big data, millions of pairs of xy, are converged into two values, beta naught and beta 1, and we get a mathematical expression y equal to beta naught plus beta 1 times x. So in future, if you know any value of x, then just substitute that into this equation, value of x, and we get a value of y. So we have simplified remembering a big data by to a small computation. So here the process is called model fitting, that is we want to make our data learn from we want to make our model learn from the data. So let's represent our whole system in vector form. So let beta be the vector representing the two values of beta, beta naught and beta 1, where x is a vector where x small x will be the data input, whereas we need one more term, so we made it 1, so we understand shortly what does it mean. So once this representation is used, now we can rewrite y equal to beta naught plus beta 1 x as beta dot x. So we can use dot product of two vectors. Now randomly select any beta naught beta 1 values and then calculate the residual sum of squares. So here for every input we know what is yi. For every input xi we know what is yi. So we just substitute that yi and find the difference between that yi and what is predicted. Predicted is this y, which is computed using beta dot xi. So subtract that. So we get an error, and these errors sometime may be positive, sometime may be negative. So the overall total error, if we are trying to calculate, we need to sum them up. Then these positive negative errors should not cancel and give us a illusion that there is no error. So to ensure that there is no negative sign, we just square this difference. So we find the difference between the actual value and the predicted value and square them and then add them all together, and that will become the residual sum of squares. The aim is to find the best value of beta that minimizes this residual sum of squares. So we need to differentiate this RSS with respect to beta and set to 0 and solve for beta, and that will result in the value of approximated value of beta as transpose of x times transpose inverse into transpose of x into y, where y is a vector of the outputs. So let's see an example here. So as you can see that there are some dots on the screen. So the x-axis talks about number of new friends, and the y-axis talks about the time spent in seconds or something. So we can see some red dots spread out all over, and if you look carefully, the overall trend is it is increasing as the number of new friends is increasing. The total number of time spent together is also increasing. So there is some trend here, and we need to understand that trend. So if we try to understand the relation between the x-axis, that is the number of new friends, and the y-axis, time spent together, then we can plot it through some linear relations. So we have drawn totally four linear relations. That means four lines are drawn together, and you can just find out which could be well representing this data. So for doing that, what we do is for any given beta naught beta 1 combination, so we get a straight line. So for that straight line, from every data point find the difference and square them, add them all, and from all the points, for all the lines, find out whichever gives minimum error. So this one looks like the one which gives minimum error, so that will be the linear approximation of our data. Yeah, of course, the data and linear approximations do not match, but anyway, the whole aim of that is to simplify the representation. So in one side we have a large number of data, xy pairs, and other side we have one simple expression y equal to f of x. And if we can use y equal to f of x, yes, it does have some error, and if that error is not making much difference to our actual processing, then it doesn't make any difference, and hence we can proceed using with an mathematical expression instead of a big data. So we get relieved with storing big data and then searching the nearest input and then finding its approximated output and all that. But instead of that, whatever input is given, we can just substitute in the mathematical equation and get the output computed. So that simplifies our activity very much. So that's we are looking at two lines. One is vertical line, one is line which is slant, and we can see that the vertical line has no relation with the data, whereas the slant line is almost passing through the data. So that will be the better approximation for the data. So we have an example here. We have data set x and y values, and then we have an R code to, to solve this. Sorry. The next one is a k nearest neighboring algorithm. So it's a simple supervised machine learning algorithm used for classification and regression tasks. Here it is a non-parametric method. That means it does not make any assumptions about any data distributions. We don't assume that their input output there is some relationship like we did in the previous case, and then assume that the two parameters beta naught and beta 1 are going to represent our data and all that. But here no such assumption is done, so it's a non-parametric approach. Here the classification of a new data point is based on the majority class or the average of k nearest neighbors in the feature space. Training phase, so there is a training phase in this case is not to identify beta naught beta 1 parameters, but just to memorize the data. Then the major part is in prediction phase. Here when a new unlabeled data is provided, the algorithm calculates a distance to all the points of the training set, and then for measuring distance, the distance metric used may be Euclidean distance, Manhattan distance, and so on. That depends on the nature of the data and the problem domain. And then the algorithm selects the k nearest neighbors, that is the data points with the smallest distances to the new data point. So in the first case, what we did, when a new point was given, from that point to all the known data, we computed the distance, and then we arranged these distances in an ascending order, and the top k values are considered. So that gives the k nearest neighbors. And if we are trying to classify, then out of these k, the majority class label among these k neighbors will be given to the new data point. So the new data point is classified into this majority class. In case of regression task, the algorithm calculates average or the weighted average depending on the situation of the target values of the k nearest neighbors and assigns this value to the new point. So in all, what are we doing is, first thing, we decide what is value of k required, that is how many nearest neighbors we want to work on, and for any new data, compute distance from new data to all the given points in the data set, and then these distances are arranged in the ascending order, and the first k data points are considered. That means these are the nearest data points. And if it is classification algorithm, so from those k data points, whichever class is having maximum number, that class will be allotted to the new data point. If it is regression, then the output values for all the k data points are considered, and average of them will be assigned to the new data point. Now the question is, what should be the value of k? So that is called the parameter tuning. Here the choice of hyperparameter k is crucial in this algorithm. A small number of k may result in noisy predictions, while a large number of k may lead to over smoothing and loss of local patterns. So the optimal value of k is often determined using techniques called cross validation. So here we have an algorithm. We example, let us look for finding the k nearest neighbors. So we find two classes, one filled in circle and one open circles. There is one question mark in between, and we want to just make sure to which class this belongs to. It belongs to the closed circle or open circle. So in doing that, what we do is we identify the number of neighbors, so that is the value of k, and then those nearest k values of the data from this question mark point are considered and then counted to each class how many belong to, and whichever count is maximum, that will be allotted to that particular class. So we are what we are doing is the hyper tuning we are trying to see. So we are just looking for various values of k. So we start from k equal to 1, then we find out what is misclassification rate. It says 28%, then for 2 it is 31%, for 3 it is 26%, for 4 it is 25%, for 5 it is 23%, for 6 it is 23%, for 6 26%, 7 25%, 8 25%, and so on. Now if you look at that, then we realize that it's in the beginning the misclassification rate is reducing and reaches a valley, and then again it starts rising. So the place where it reaches the valley, that is with k equal to 5, we are getting the best results. So we continue with k equal to 5 in future predictions. So that's what we have plotted. So that's the advantage of working with visualization. So as long as we are showing this data, it's difficult to discuss what I am telling. It's difficult to communicate what I am trying to convey, and so you may not be able to follow. But instead of that data, if we shift it to this graph, then you can easily see that the minimum is somewhere 5 or 6. So with k equal to 6, we get a best possible result. Therefore, we can find best predictions when we work with the KNN using k equal to 6 or 7. So that's KNN. The first two methods what we have seen. The first one was linear regression. Second one is KNN. Both cases it was given with the output along with the input. So these two are the cases of supervised learning. Whereas now let us see one example of unsupervised learning where only input data is given. There is no labels attached to it. So one of the popular unsupervised learning method is the clustering methods is k-means clustering method. So this can be used for clustering customer segmentation, image compression, anomaly detection, pattern recognition. Many such things are possible with this. So in the k-means, what we do is we first initialize the algorithm by randomly initializing k cluster centroids in the feature space. These centroids represent the initial guess of the cluster centers. Then assign each data in the data set to the nearest cluster centroid based on some distance metric. Usually Euclidean distance is used. or it can be Manhattan depending on situation. There are many other distances metrics are there. So depending on different requirements, different metrics are recommended. So here it can be a simple Euclidean distance. These data points are assigned to the cluster whose centroid is closest to them. Once every data is assigned to nearest cluster centroid, then we update the centroids again. So depending on how many data points are assigned to one centroid, so taking all those data points, a new centroid is computed. So this happens for every cluster. And then this after redefining the cluster centroid, then again assigning the data to the nearest clusters is repeated. So after assigning, redefining the centroid, so this process 2 and 3 gets repeated until there is no more change in the data from one cluster to other cluster, that is unless till it converges, this process will continue. So in each iteration, data points are reassigned to the clusters based on the updated centroids, and the centroids are recalculated based on the new assignments. The algorithm continues iterating until convergence. So the convergence is a situation where the centroids stabilize and no longer change significantly between iterations. So there is no more shift in the centroid position. So then the algorithm can terminate. Now the output is the k-means algorithm is a set of k cluster or centroids and assignment of each data point to a cluster. These clusters represent group of data points that are similar to each other and dissimilar to the data points in the other clusters. So that means all the points within the clusters have some similarities, and 2 points which belong to two different clusters don't have any similarities, they have more dissimilarities. So looking at this, so if you start looking from the bottom left, so you see that all the points are black. Then we start with the three centroids, that's the second line on the bottom. Green, red and blue points are there. Then as we see, the one cluster is nearer to the blue, so all the upper points are labeled blue. The next one, the central cluster, some of them are near to the red, some of them are near to the green, so some are green, some are red. The lower cluster all are near to the green, so that's what happened. Now we have three colored clusters. Now for these three colored clusters, calculate the centroid again, and then we continue this process again. So if you look at the last in the lower part, we still see that some green points, red points are still there in the central cluster, and the number of green are reduced, number of reds are increasing. Finally on the last one, the upper right, we can see that one cluster are totally blue, another cluster are totally red, and the third one are totally green. No more mixtures are there, so it has reached the it has converged. So we stop there and we define that the whole thing is made up of three clusters. Again same thing comes is defining what should be the value of k. So the value of k definition is more art than a science. So that's a number of data you have n, so it has to be between 1 and k, 1 and n only. So these convergence issues, there are some convergence issues which solution can fail to exist if the algorithm falls into a loop, for example, keeps going back and forth between two possible solutions, or in other words, there isn't a single unique solution. Then interpretability can be a problem. Sometimes the answer isn't at all useful. Indeed, it is often the biggest problem. So, in the problem with associated with k means is choosing k is a big problem, and sometimes a convergence may not be possible. It may take almost infinitely large number of iterations to converge because we are dealing with infinitely large number of data sets. So because making sure that everything fits well, so it may take very large, and in doing so it may get into a loop also. And knowing that we had entered into a loop is difficult, therefore it gets again and again and again into the same. So that will be one problem, so we may not come out with any solution. And even if we come out with solution, so it's not looking at the input output through the realistic or real world situation. It's just taking them as a numbers and manipulating the positions and all that by the machine. So it may not have any proper interpretation of what the results are talking about. So that may be another problem we have. So that's all for now. So that's the end of module 2. We have many more things coming. So let's jump into module 3 in the coming session. So till then, keep watching. Thank you.